Welcome to iLecture Online, and here's a second example of a torque problem. Again, it's a static problem, meaning nothing is moving, nothing is accelerating. The sum of all the forces on this problem are 0, and the sum of all the torques on this problem are 0. And so the concept we're going to use here is that the sum of all the torques about a chosen pivot point must add up to 0. And I'm going to pick this pivot point right here to start off the problem. So we're going to pivot everything about this point. We have to identify all the forces acting on this problem and what the corresponding torques are of each of those forces. So let's identify the forces. First of all, we have the weight of this mass hanging from the beam, and we'll call that mg. And notice if this is the line of action of that force, the distance from the pivot point to there, this is this distance right here, that would be considered the distance associated with that force causing that torque. We have a second force acting. It's the mass of the beam itself, and the mass of the beam acts as if all of it acts through the center mass, and so we have the big mg coming down this way, big mg, and therefore the line of action of that force is this line right here, and this distance from that point to that point could be considered distance 2, the perpendicular distance associated with the second force. Okay, now the third force would be the tension in the cable right here. The tension in the cable is pulling this way, and so this would be the line of action of that force right here, and this distance from there to there could be considered distance 3, the distance to the line of action of the tension in the cable. And I believe those are the only three forces acting on that particular beam, and we're now ready to go ahead and try to solve the problem. So we can say that the sum of all the torques add up to 0, so let's find all the torques. Let's find torque number 1 caused by the little mg right here. And I'm going to define clockwise torque as positive, counterclockwise torque as negative, and if this was the only force acting on the beam would be pulled in a clockwise direction. That's a positive torque. And then the distance from that line of action to the pivot point is distance 1. So I do it like this first because I don't want to get my brain all cramped up trying to figure out what D1, D2, and D3 are right away. I'll do it one step at a time. First, I want to get the correct equation on the board. So the second torque is caused by this big mg. It's acting downward, so it would cause the whole beam to swing in a clockwise direction. I call that a positive torque, so plus big mg. And I multiply that times the distance from the line of action of that force to the pivot point, which is distance 2. And finally, I have this tension pulling in this way. If this was the only force acting on it, would pull the beam in a counterclockwise direction, so I call that a minus tension, times the distance from the line of action of that force to the pivot point, which is this distance right here, which is distance 3. All right, so now at least I know I have the correct equation on the board. Now I simply have to find out what D1, D2, and D3 are equal to. So D1 is this distance right here. So I have a triangle right here. Let me draw the triangle right here on the side. So there we go. There we go. There we go. This here is distance 1. This length right here is 4/5 the length of the beam, because if I attach this at 1/5 from the end of the beam, then this port right here is 4/5. So this is 4/5 L. This angle right here, theta, if it's 45 degrees, that's equal to this angle theta right here. That's the same. So alternate interior angles are equal, so I'm going to use this angle right here as being theta. And since D1 is opposite to the angle theta, I can say that D1 is equal to the hypotenuse, which is 4/5 L, times the sine of the angle theta. And that goes in for D1. All right, so we have 0 is equal to mg times D1, which is 4/5 the length of the beam, times the sine of the angle theta. There we go. Plus, now we have big mg times D2. What is D2 equal to? Well, D2 is this side of this little triangle right here. So let me draw the little triangle right here. We have D2 here. We know that this angle is 45 degrees. That means this angle here is theta as well. And the hypotenuse is half the length of the beam, so that's L over 2. So I can say that D2, which is opposite to the angle, is equal to the hypotenuse, which is L over 2 times the sine of the angle theta. So that goes in here. So that's 1/2 the length of the beam times the sine of the angle theta. And finally, I have minus the tension times d3. Now to find d3, I will draw this triangle right here. So I have this triangle, which is like this. We have this angle here, which is theta. We have the length of the beam, which is L. And I want to know what d3 is right here. And notice that d3 is adjacent to the angle. So I can say that d3 is equal to the hypotenuse L times the cosine of the angle theta, since d3 is adjacent to the angle. And that goes in here. L times the cosine of the angle theta. All right, now that we have all that, we can solve this equation for theta. Notice that every term has the length L of the beam in it, so that can cancel out. So this L, and this L can cancel out. Now I move the minus t cosine theta to the other side of the equation. That becomes a plus t cosine theta is equal to mg times 4/5 times the sine of theta plus big mg times 1/2 times the sine of theta. And finally, I can now divide both sides by the cosine of theta. I can factor out a sine of theta, and I can factor out a g. So I can write that t is equal to m times 4/5 plus big M times 1/2. Multiply this times what I factor out, which is g sine theta, and divide the whole thing by the cosine of theta right here, which is equal to sine of theta divided by cosine of theta is equal to the tangent of theta. And so what I have here is that t is equal to 4/5 times the little mass plus 1/2 times the big mass, all times g, all times the tangent of theta. And now I can plug in what those numbers are equal to. So this is equal to 4/5 times the little mass of 50 kilograms plus 1/2 times the mass of the beam, which was 200 kilograms. Did I write that down somewhere? I didn't. I meant this to be 200 kilograms, so big M is equal to 200 kilograms. That's the mass of the beam. Okay, so 200 kilograms. Okay, so that's what's inside the parentheses. Now we multiply that times g, which is 9.8 meters per second squared. And then I multiply this times the tangent of 45 degrees. And the tangent of 45 degrees is equal to 1. So, like that. So now we need a calculator to figure out what those are equal to. Okay, so we have 50 times 4 divided by 5. Add that to half of 200, which is plus 100. And multiply that times 9.8. And multiply it times 1. And so it turns out that the tension in that cable is equal to 1,372 newtons. And that's the answer. And that's how you do a problem like that. So again, to summarize, you know that this is a statics problem. You're going to use the principle that the sum of the torques add up to 0. Then you have to find each of the torques, which is the force multiplied by the perpendicular distance, the distance from the pivot point to the line of action, the perpendicular distance. And so what I always do is I write d1, d2, d3, and so forth first. I note them on the graph to show you what they are. And then later on, I go find out by drawing my little triangles what those distances are equal to, and then plug them in. If you don't do it that way, it sometimes gets very difficult to get that equation correct on the board. And the rest of it is simply algebra, and there you go. So that's how you do a torque problem that looks like that.